Hi, good morning.
Mine.
Sorry for
Good.
postponing this session, but uh, yeah, and also letting you guys know in the last minute. All right. As said, I was expecting Mr. Tony to take this session, but then he isn't available. That's why we decided to go with this session. All right. So we can discuss any doubts regarding week 9, or for that matter, like if you have any questions. So I think Muttu or someone was asking me some question last time from other week lecture. So if you have any such questions, feel free to ask now. We can have a discussion on that. All right, so let me open the slides. Yeah, slides are with me. uh, yeah, please go on if you have any questions.
Yes, ma'am. Week 9, lecture 3.
Let me just open. So, could you tell me the topic, please?
Yes, ma'am. It is to the formulas for coefficients and Fourier transform.
Formulas for coefficients. Okay. Okay. Fourier transform properties. Let me share my screen so that you guys can let me know if that is. Could you see my screen? Is this what you are having doubts with?
Uh,
Hello.
I think the one before.
Uh, which one? For so proper. You mean here?
Before this. Uh,
So
yeah, yes, I
here,
think. It's,
here is where
um,
Fourier transform is beginning. So this is just an introduction to what exactly we mean by the Fourier transform. We have Fourier series representation for the periodic signals. A similar kind of Fourier analysis can be done for the aperiodic signals. And one such analysis is the Fourier transform, which makes our life simpler in the frequency domain instead of working in the time domain. So, Fourier transform is something that gives us the relationship between the frequency. So, this is one to one mapping, whether you work with the time domain or whether you work in the frequency domain, things go in the same fashion, but a lot of complicated things in the time domain can be seen simpler in the frequency domain. So that's the idea behind Fourier transform. We have Parseval's theorem, and there are certain examples for the Fourier transform, and here are certain properties of Fourier transform. Yeah.
yes, ma'am. In the slide one before,
This one
the aperiodic projection.
here. Hmm.
Yes, ma'am. Yeah, here. So
Yes.
here, ma'am, in Z of t,
Hmm.
uh, we are taking nu as the frequency, right?
Uh, yes, you
Mm.
asked the frequency, correct.
But while in the next step, why we are having omega as the one?
Oh, okay. So let me clarify this point. So Z of t is equal to either integral over AV EJVT dV, or you can also represent this as A omega E J omega T d omega. Okay.
Yes,
So
ma'am. Yes,
that's
ma'am.
all right. So just V is replaced with omega. That's all
Change in
happened
value.
here. Yeah. So when you multiply you know two signals, like you can write this in this way, right? I mean, you're taking double integration. So this is one. What I mean is, by Parseval's theorem, you know that uh, uh, what is this? So basically, the idea behind this is, so this z of t whole square can be represented as this product terms. So this corresponds to one z of t and this corresponds to the other z of t. And when you do it with respect to dt, there's some representation over here which says this, and you can just prove it to be this. I haven't gone through this lecture, but I hope the the lecture video would have given every detailed step for this, right? But to answer your question, it's just some notation wise. So the same z of t can be represented as z omega e j omega t, and we all know that mod z of t whole square is equal to z of t times z star of t, which is the conjugate version of that signal, right? So that is what is being written over here, but I hope the detailed calculations would have happened in your lecture video. Does that answer your question, or do you still have the confusion?
Uh, yeah, ma'am. In second line, we are taking just the inner product, right?
In the
With
second
zeta,
here,
yeah,
yes, yes.
zeta
So
t.
mod z of t square, this can also be written as the so this is, yeah, this is exactly the inner product, and that can also be written as z of t times the conjugate version of the signal.
Yes, ma'am. So while taking the z of inner product, why
Hmm.
in z of t we are considering the frequency to be in one notation, that is nu, and in the phasor, that is e power minus j omega t, we are having the frequency in another notation, that is omega.
So I think the reason why professor used a different notation omega is, in certain cases people get confused. Had it been dv, you would have written it av. So if the think of this as dv, so you are integrating it two times, right? So z of t is a signal that is, let me write it in my notes and share. Uh, so I hope you're able to see my screen, right?
Yes, ma'am.
Yeah, these are certain integration things, by now you guys should be comfortable enough. So z of t is integral minus, maybe he hope to say it is over entire, minus infinity to infinity, av e power j v t dv, right? This is what is given. This is also same as integral minus infinity to infinity a omega e power j omega t d omega. So could someone tell me what is z star of t, the complex conjugate version of the signal is integration from minus infinity to infinity a v star e power minus j v t dv, correct? So
Yes,
when
ma'am.
I have to multiply z of t with z star of t, so how do I do that? Minus infinity to infinity, a v e power j v t dv, integral minus infinity to infinity, a v star e power minus j bt dv, correct?
Yeah, yes.
So when you have to do this multiplication, it's often confusing to, have them in the same uh, thing. I mean, you can try to understand with some example. Suppose, z of t. Let me go to discrete time domain. Suppose if it is a0 uh, e power z0 t plus a1 e power j1 t plus a2 e power j minus 1 t. Let me call some example, okay? Now, what is z star of t? Z star of t is a star e power j 0 t plus a1 star e power minus j 1 t plus a2 star e power minus j minus 1 t. When you have to multiply these two things, how would you do that? So every component is multiplied with every other component, right? So if I, or a0t into z star of t plus a1 e power j1t into z star of t plus a2 e power j minus 1t into z star of t. So every component is multiplied with every other component. So often in integration, what happens is when you write it in terms of like this, as you know, that integration is something, that can be, uh, you can also write this as av av star e power jvt e power minus jvt dv dv, correct? So I can just interchange the integrations, right? So when I use the same variable, what happens is, like in the notation wise, these two things get cancelled with each other, and what you will be left over with, minus infinity to infinity, minus infinity to infinity, av av star dv dv. This is not correct at all. You see the point, right? I even
Yeah,
gave you
yes,
the
ma'am.
example of the
Yeah,
discrete
yes.
version. So this is not true at all. So when you are working with, multiplications of such integrations things, the correct answer or the correct representation is, change this variable to some v prime. And now what happens is minus infinity to infinity av av prime star e power j vt e power minus j v prime t dv dv prime. So this is the correct answer. Only when v and v prime are equal, you get some things. When they are not equal, you have to multiply with the different frequencies. Even when uh, you know, when you take the same frequency signal and when you try to multiply them, you have coefficients even at the added or the subtracted frequencies. So this is some simple thing. I mean, this is something related to integration. Okay.
Yeah, yes, ma'am.
Yeah. Good. So, any other questions regarding week 9? Is your assignment deadline extended? Like I requested the team to extend the deadline. I am here today till 10. Okay. Yes, I requested the team to extend the deadline. So, did they extend the deadline by a day? Because this live session was supposed to happen yesterday, right? Which got postponed. So, I also requested the team to postpone the assignment. Did they extend?
Not yet, ma'am.
Oh, they did not? I see. Okay. Any difficulty in solving the assignment?
Yes, ma'am.
So could you tell me like which exactly are you facing? Like which questions are you facing the difficulty with, so that I can help you with some hints to such problems?
Question 4 and 5.
Okay, let me open the assignment. Uh, Graded assignment, right?
Practice.
Practice assignment, which question?
Question 4 and 5.
Okay, so I mean, what exactly is the difficulty that you experienced with this question? Could you tell me? So let me write the question. I hope this is the question. So you are supposed to find the Fourier transform of the signal x of t is equal to del of t minus 2, which is denoted by x of j omega. Now you're supposed to find the magnitude of x of j omega whole square. So this is what you're supposed to find. So what is the difficulty that you experienced?
How to apply Fourier transform? Like,
Okay,
still difficult.
so we know that Fourier transform of unit impulse is 1, right? Yeah, this is something that we know.
Yes, ma'am.
And we know according to the shifting property, so if x of t has Fourier transform x of j omega, then the Fourier transform of x of t minus t naught, okay, where this is x of t minus t naught is a time shifted version of x of t. This has Fourier transform e power minus j omega t naught x of j omega, correct?
Yes, ma'am.
This is known as time shifting property of Fourier transform. Okay, so using that property, now the Fourier transform of del of t minus t naught, t minus 2, is nothing but e power minus j omega times 2 Fourier transform of del of t. This is simply 1. So this is e power minus 2j omega, right? So for the given signal x of t, which is del of t minus 2, x of j omega is e power minus 2j omega. This can also be written as cos 2 omega minus j sine 2 omega, correct? Now the magnitude of this is square root of cos 2 omega square plus sine 2 omega square, correct? Which is nothing but 1. Now what happens to x of j omega square? 1, right? So that's all right. Like, what exactly is the difficulty you faced in these steps? Could you tell me?
Fourier transform. I'm confused between Fourier transform and Fourier series. That's why.
Okay. So, yeah, simple. Fourier series is represented only for periodic signals. Fourier series is only given for periodic signals. Okay, you have to practice a lot with the notation and representation. And what exactly is the Fourier series? So it'll be something. So if x of t is a periodic signal with period t naught, then its angular frequency is omega naught, which is equal to 2 pi by t naught. Then for this x of t, it can be represented as always some infinite sum of complex exponential signals. Okay, so this is the definition of Fourier series. So for any periodic signal, so I'm trying to just open the Fourier series slide so that I'm not making. Yeah, any periodic signal can always be represented as sum of the complex exponentials. Any periodic signal. So this is the Fourier series, and this is the representation of the Fourier series, where AKs are given as 1 by T naught integral minus T naught by 2 T naught by 2 uh, x of t e power minus jk omega naught t dt. So this is Fourier series. Okay, any periodic signal. So you should not forget this thing. So for any periodic signal, we have the Fourier series representation. Now going to the Fourier transform, and using this representation, we have several properties over here. Suppose x of t is a periodic signal, then x of at, I mean time version at plus b will also be a periodic signal, right? We know that because shifting will not change the periodicity of the signal. So x of at plus b also will be a periodic signal, and based on that, if ak's are the coefficients for the signal x of t, you can do, there are certain properties on what happens. So if you call this as y of t, you can, like, if this has coefficients bk, you can relate the coefficients bk's and ak's. So those are certain properties for Fourier series. Now going to Fourier transform, okay, what it says is every signal x of t, irrespective of the periodicity, every signal x of t under certain conditions, which are called again Dirichlet's conditions for the Fourier transform, every signal x of t under Dirichlet's conditions, Dirichlet conditions are sufficient conditions. There are few more signals which do not satisfy Fourier Dirichlet conditions, but they still have Fourier transform. But for now, for this course purposes, we can understand Dirichlet conditions. Any signal satisfying Dirichlet conditions will have a Fourier transform representation. What it means is there is an associated frequency domain. So this is in the time domain, right? So x of t is a signal that you represent in the time domain. Maybe let me call this as x of t. Okay, corresponding to this x of t, there is a frequency domain representation. Okay, and in this frequency domain representation, which we denote by omega, the signal may not necessarily look like this. It could be some other signal, you know, it could be some other signal. Okay, so I'm drawing it very badly, but like what it means is every signal x of t, it has a different representation in its frequency domain. And how are they related? So x of j omega is minus infinity to infinity x of t e power minus j omega t dt. Remember, this omega is not the fundamental frequency, whereas here if we see in the Fourier series representation, that's why I wrote it in omega naught terms. Omega naught is the fundamental frequency. So this isn't the different frequency representation. Fourier series tells us that only like when the signal is periodic, we can write it as the infinite sum of the complex exponential signals. But both are in time domain. You need to understand that very carefully. Both are in time domain. So this is in time domain and this is also in time domain. So it's just an alternative way of writing it. But whereas Fourier transform tells that for every signal which satisfies the Dirichlet conditions in the time domain, there is other representation in a completely different domain, in a completely different space, not here. So it's like, maybe you will be weighing some weight on the earth, but you will be having a different weight on the moon. So it's similar to that. So in the time domain, the signal is represented in this fashion, but it has an alternative representation in the frequency domain. Right, that is what Fourier transform says. And what is that alternative representation? So in the frequency domain, the signal is represented like this. So when you do an integration and when you get the signal in the frequency domain, so this integration is over all the time values. So at the end, all the time, so that there won't be any time, what you will be left over with only the frequency. And this is what the signal looks like in the frequency domain. And you can always, so this is a one-to-one mapping. You can, so for every x of j omega, for every signal in the frequency domain, there is a signal in the time domain. Likewise, for every signal in the time domain, there is a signal in the frequency domain. Under Dirichlet conditions, there are few more conditions, but Dirichlet conditions are sufficient conditions to check at least for this course. Okay. So, and how do you come back from frequency domain to the time domain? You have to do something like this for the frequency domain signal. Okay, I'm repeating again, this omega is not the fundamental frequency. This omega is the complete different domain, so which is called the frequency domain. Whereas in Fourier series, you only within the time domain, like you stay only in this domain. Within the time domain, this x of t analytically can be represented in a different way, so as to make our calculations simpler, that's all. But we only act in the time domain, whereas for the Fourier transform, we go from one domain to a different domain, which is called frequency domain. And under certain conditions, every signal x of t, irrespective of the periodicity, every signal x of t has one-to-one representation in the frequency domain. That is what Fourier transform is telling. And under this transformation, so this transformation is known as Fourier transform. Why do we do this transformation? Maybe you will be you will be weighing heavy on the earth, but you may not be weighing heavy on the moon. So when you don't weigh heavy, maybe there are certain benefits, because you don't weigh weigh as much as you weigh here on the earth. So like when your weight is less, like there are certain benefits. So that's the reason, like when certain things are complicated in the time domain, when you look at the same, same signal frequency domain, there are a lot of benefits. Like for example, del of t del of t is a complicated signal to understand, right? Because like, what is del of t? Like, it has infinite area at 0. All we know about this function del of t is minus infinity to infinity del of t dt is 1. This is all we know about the del of t function. But how do we visualize this function in the time domain, right? But when you go to the frequency domain, when you find the Fourier transform of del of t, so this is simply 1 in the entire frequency domain. This is simply 1. Okay, so whatever the signal visually looks complicated in the time domain, you can see by applying a simple transform, looks so clean in the frequency domain. So instead of working with the del of t in the time domain, it's always beneficial to work in the frequency domain, because like we can understand the signal much more clearly in the frequency domain, right? So this is like one simple example. There are several examples like that. By like, lot of things which look complicated in the time domain, they look, uh, amazingly simpler in the frequency domain. So this is like an amazing transform, and the transform is 1 to 1. So instead of working in the time domain, you can go to the frequency domain and work in the frequency domain, and at the end you can come back to the time domain, and things just work simple. They just happen to work magically. So this is a beautiful transform. Everybody should appreciate it. Okay. Yeah. So this is with the Fourier transform, and for this transformation, there are several things. Like suppose x of t has the Fourier representation x of j omega Fourier transform. Then what happens to the Fourier transform when you shift the signal? uh, we can analyze using the transform. So what is x of j omega? X of j omega is given as integral minus infinity to infinity x of t e power minus j omega t dt. Now what happens to Fourier transform of x of t minus t naught? This would be integral minus infinity to infinity x of t minus t naught e power minus j omega t dt. Let me call this as t prime. So t prime is equal to t minus t naught, dt prime is equal to dt. Likewise, t is t prime plus t naught. When you substitute, what you get is minus infinity to infinity x of t prime e power minus j omega t naught e power minus j omega t prime dt prime, which is simply e power minus j omega t naught integral minus infinity to infinity x of t prime e power minus j omega t prime dt prime. So this part is simply the Fourier transform of the original signal x of t. So this is e power minus j omega t naught Fourier transform of x of t, which is nothing but x of j omega, right? So likewise, you can do all sorts of things. When you have the differentiation, so this is known as the time shifting property of the Fourier transform. When you do differentiation in the time domain, you can find what happens to the signal in the frequency domain. While you do integration in the time domain, you can find what happens to the signal in frequency domain. And there are lots such properties for this Fourier transform. I hope it is clear. Yeah.
Yes, ma'am. Yes, ma'am.
All right.
Ma'am,
Yes.
uh, so how it results one if we get the Fourier transform for the delta signal?
Sorry, could you repeat it?
Yes, ma'am. So how we get one if we do the Fourier transform for delta signal?
Just plug in what happens. So Fourier transform of del of t is what? Integration from minus infinity to infinity del of t e power minus j omega t dt, right?
Yes, ma'am.
Just plug in and this should yield you 1 because del of t exists only at 0. This is same as integral minus infinity to infinity del of t e power minus j omega times 0 dt, right? Because just the property of the delta function. What is the property? Del of t minus t naught some f of t is what? Del of t minus t naught f of t naught, right? We learned this in our earlier sessions. This is the property
Yes.
of the delta signal, and consider t naught to be 0 and f of t as this, right? And what is this? This is simply del of t dt, which is 1, correct? This is not difficult.
Yes, ma'am.
This is simple.
Yes.
But the confusion lies while you find the Fourier transform for the unit step function. This is not very straightforward. You have to write unit step function in terms of the delta signals and then you have to analyze. I hope sir did it in your lecture videos. So this is not very straightforward. So yeah, you shouldn't be confused with finding the delta Fourier transform for the delta function. But like try to understand the Fourier transform, how it came for the unit step function. I'm not going to do this, but this is an important thing, okay? It's already done in your lecture video.
Yes, ma'am.
Ma'am,
Yes.
just delta function which you write no.
Sorry, I didn't understand.
Just before the delta function, could you scroll up?
Sorry, could you
Little
repeat it again?
Ma'am, could you scroll up little bit?
Could
The
I
slides.
explore what slides?
No, no.
Hmm?
This slide. Scroll.
Scroll. Okay.
Yes, ma'am. Where here you write xt dash and e to the power j omega t dash and dt
Mm,
dash. In
mm, mm.
then how could you say that this is the Fourier transform of xt?
No, that's just change of variables, man. You shouldn't get confused with the change of variables after doing signals and systems course. So, like, what is this? This is just, so this can also be written as integral minus infinity to infinity x of t e power minus j omega t dt, right? They both are the same. Whatever I am highlighting in yellow, this is same as whatever I have written here. They both are same.
Okay, got it.
Okay. Yeah. All right. Any further questions? So you also have doubt in the fifth question, right? So let me open the fifth question. Okay. So what is the fifth question? Fifth question is just the shifting property. There's nothing more to this. So it's just what we discussed here. Shifting, time shifting property. Straightforward.
Yes, ma'am.
This is a beautiful transformation. Please learn it, like, yeah, it's a very good transform. Any further questions?
Ma'am, could you explain the duality of Fourier transform?
Okay, duality. Maybe I don't have the proof in hand, but I could explain like what the duality properties is stating. Let me open it. Okay. So what duality? Duality is again an interesting property of Fourier transform. I hope professor did the proof in the lecture video.
Yes, ma'am.
So you can see that, but I would just explain what this property is. Okay, so what this property says is, suppose x of t has Fourier transform x of j omega. I don't know what happened to my writing today. Okay, where x of j omega is the Fourier transform of the signal x of t. Okay, now x of jt. So okay, so you have a signal x of t, maybe something which looks like this. Okay, that has a different representation in the frequency domain, right? Maybe let me call it to be like this. Okay, so this signal x of t has some representation in the frequency domain, which we are calling x of j omega. Okay, yeah. Now when I take the same this signal, when I take it in the time domain, which I call x of jt, this has a frequency domain representation as this. If it is confusing with the x terms, let x of t has Fourier transform. What shall we call? Let's call it to be some. What do we call? Let's call z. Is that okay? Okay, let x of t has the Fourier representation z of j omega. I mean, x of t in the time axis is represented as z of j omega in the frequency axis. So the z is also another signal, right? When I take the z signal in the time axis, okay, so I'll also explain to you in with an example. When I take this z signal in time axis, the Fourier representation of that signal is this. So let's take this delta function. Okay, so delta function is represented in time axis like this. So this is del of t. This has the Fourier representation 1. This is Fourier transform of del of t. We let us call it x of j omega, this as x of t. Now we are asking the question, what happens to the Fourier transform of x of jt? So when I take, so this is in the omega axis, when I take the same signal, the same constant signal in time axis, the question is, what happens to the frequency domain representation of the signal? The frequency domain representation of the signal is 2 pi times x of minus j omega, which is 2 pi times del of minus j omega. This is same as 2 pi times del of omega. So the Fourier transform of this signal, the constant signal, is nothing but 2 pi times del of omega. Is that okay?
Yes, ma'am.
Yeah, that's how you have to analyze. So if x of t has the Fourier representation x of j omega in the frequency axis, whatever the signal that you see it's like when your weight is 49, this is like a stupid example, but I would like to compare. Say your weight is 50 kgs on earth, maybe your weight is 30 kgs on the moon. Okay, so like you want to see uh, how the 30 kg person on moon, sorry, the 30 kg person on earth looks like on the moon. Okay, so it's the same analogy. So uh, x of t has some nicer representation in the frequency domain, and when you take that nicer representation like that into the time domain, the question is what happens to its frequency domain of that nicer form. So that is what duality is stating. This is how it looks like. Okay.
Yes, ma'am. Clear.
Yeah, any further questions?
Ma'am,
Yes.
how the time axis is defined in the uh, frequency domain?
Oh, no. Time axis is not defined in the frequency domain. All we are telling is, say, what example shall I take? Maybe let's take the sync function. Okay, so this is some sync t. We all know that sync functions frequency domain representation is a rectangular signal, right? If I'm not wrong, I think this is something that was proved in your lecture video. If I'm correct me if I'm wrong, but there is a one-to-one correspondence between the sync function and the rectangular function. So if you call this as x of t, this is your x of j omega. Okay. So now what duality property is telling is, take this rectangular function. Yes, Muthu.
Ma'am,
Yeah.
is this isn't it the other way, ma'am? Because
Yeah,
the
correct me if I'm wrong. Yeah, that's what I'm telling. I don't remember this exactly. So for the rectangular function, it is sync in the frequency domain, huh?
yes, ma'am, I think yes.
Yeah, could you check this and correct me? So what happens to this? Let
Yes, ma'am.
let
The frequency, the Fourier transform of rectangular pulses, the thing.
Okay, Fourier transform of the rectangular. So if I take a rectangular function, let me call this x of t. Its Fourier representation is the sync function. Okay. Now we are not looking for the time axis in the frequency domain. What we are telling is, take this entire signal, get that signal, plot the same signal, whatever you are seeing there, plot the same signal in the time domain. Whatever you just saw in the frequency domain, plot the same signal in time domain. Call it some y of t. Okay. So if this is the case, then duality property says, with some change in the coefficients, for this signal in the time, whatever that you are seeing, the frequency representation of the rectangular function in the frequency domain, when you get that same signal into the time domain, get the same signal into the time domain, plot the same signal in the time domain, then for this signal, the frequency representation would be like this with some scaled terms. Is that okay?
Yes, ma'am.
With some
And
scaled
ma'am,
terms.
when we put it into the time graph, the y of t,
Mm.
so at which point it comes
This is
So
x
how
of
to
jt.
determine it?
Oh, no,
Yeah,
exact
it's
same points. Exact same points. So x of so this is x of jt. So this is how you're supposed to plot this. So this is your x of j omega. In the time axis, you
yeah.
plot x of jt.
Okay. So if something is there on one point one on the frequency domain, it comes the point one on the
Exact,
time domain.
yeah, time domain. Yes, correct.
Okay. Yes.
Okay, it's with some scaled version, and what this would be 2 pi times x of minus j omega, and we know little x is our rectangular function, so with some scaled terms it almost looks like the rectangular function. That's the idea behind the duality. Okay.
Yes.
Yeah, any further questions?
Ma'am,
Yes.
for a finite time signal, the Fourier transform will be infinitely long, right? And the other way is also true.
Yes, you can assume it to be like that one. True.
Yes, ma'am. So it's hard to intuitively understand it. So how is it coming out to be a fact actually?
Fourier transform is this, it's you're asking me the question on how did someone came with such a transform. Yeah.
Yes, I mean
you
in
can
one
do
domain
you
it is
can do that
like
as a reading assignment. Okay, you can go dig in Google,
yes,
how did Fourier even came up with this transform. It's a beautiful transform. How did this happen intuitively? How did Fourier
yes,
think about it? You can do this as a reading assignment, I say. Okay.
yes, yes.
Any further questions? Please practice these things. Apart from the teaching, you understand them well only when you practice a lot. So please practice. Yeah. Professor and also other teacher Tony. Okay, Prof Tony also will be attending this live session probably in the next week, who is the one behind setting up your week 9 assignment. If you have any further questions, like, feel free to ask them in the next live sessions. I'll also be present. Okay.
Yes, ma'am.
Um, how can we get access to the MATLAB code that professor demonstrated or made use of in the lectures?
Sorry, MATLAB code. Uh, I am not sure if the
Yes, ma'am.
professor is sharing the MATLAB code because, like we said previously, this course. So MATLAB is only being used for instruction purposes. So it's only being used for instructive purposes, not for. So this course is not meant to teach MATLAB. I think henceforth they may not upload the MATLAB codes, but anyways, I'll check with the team and let you know. Okay.
Okay, ma'am.
Yeah. Not really sure if the codes will be shared in this course, but yeah, I'll anyways check with the team. Okay. And we'll upload if we can upload. All right. So if you have no further questions, can we break this session? Please practice a lot. Yeah. If you have any difficulties, we can talk in our next live session on Wednesday. All right.
Yes, ma'am.
Thank you,
Thank
ma'am.
you. Thank you guys for attending, and sorry for postponing this to the morning. Yeah.
Yeah, no problem.
Yeah. Thanks. Bye.
Thank you.
Okay.
Yeah,
That's fine.
thank
Thank
you.
you.
Bye.